Hi, welcome back to our foundation series on physics. Let's do a quick recap of what we discussed in the earlier lecture and then take up a new topic today. In the earlier lecture, we discussed a current carrying conductor creating a magnetic field around it. It is a temporary magnet. It is an electromagnet. We discussed the various properties of a electromagnet, the similarities and differences between a permanent magnet and an electromagnet, some applications of electromagnets. Many of these concepts were illustrated through simple experiments that I showed you. Then the rule that we can use to determine the direction of the magnetic field of a wire carrying current, the right-hand thumb rule as it is known. And we compared the magnetic field lines of a solenoid with that of a bar magnet. They look similar. So these were some of the things that we discussed in the earlier lecture. Moving ahead, this is a very simple question I'll ask you. What would happen if I brought a magnet which has a magnetic field around it and kept it near another magnet which also has a magnetic field around it? When they are brought close to each other, there may be a force of attraction, like in this case, or repulsion if like poles are brought near each other. So one permanent magnet exerts a force on another permanent magnet. And this is something that we have all seen, even in childhood. Playing with magnets, you've seen that you bring two magnets close to each other, there is a force of either attraction or repulsion. This is something every one of us has experienced. But what would happen if we brought an electromagnet? Remember, an electromagnet can be created simply by having an electric current flow through a conductor. Now this is a circular loop, and we have seen that it creates a magnetic field around the loop. But for all practical purposes, it is a magnet. What would happen if we bring this electromagnet with a magnetic field around it near a permanent magnet, which also has a magnetic field around it? This also was answered by a demonstration that I did for you in the previous class. There will be a force of repulsion or attraction, because even though one is a temporary electromagnet and one is a permanent magnet, they are magnets, and there will be a force of attraction or repulsion because both magnets have north and south poles. So clearly, when a current carrying conductor, and this is our current carrying conductor, which was converted into a temporary electromagnet because of the electric current, is brought near a permanent magnet, and this is our permanent magnet, then they exert a force on each other. It could be attraction or repulsion. So clearly the wire carrying an electric current in the presence of the permanent magnet experiences a force. Let us look at a simple experiment that illustrates this even better. So what are we doing in this experiment? We have a permanent magnet And this permanent magnet obviously has a magnetic field around it. And we have a battery here, and the wires from the battery are connected in this way to complete the circuit. So current is flowing through the conductor, which has been freely suspended. Now, where is this conductor freely suspended? It is inside a magnetic field. Inside which magnetic field? It is inside the magnetic field created by the permanent magnet. Right? So the permanent magnet has a magnetic field like this, and our current carrying conductor has been placed inside that magnetic field. So now we have two magnets here. One is the permanent magnet and one is the temporary magnet. And where is our temporary magnet? This one. And we have allowed it to move because it is freely suspended. So what will happen? Let us see what happens in this case. So this is a setup very similar to what I described. We have here the black one, the big circular object here is a permanent magnet, a very powerful permanent magnet. Suspended inside the magnetic field is a copper rod. Now the copper rod will have wires running to the battery. Let us see what happens when current flows through the copper rod. So that see that again, the wire is moved, the wire is pushed aside by a force. Now, why would that happen? Like I said earlier, we have two magnets in this situation, the permanent magnet and the temporary magnet, and one exerts a force on the other. They are exerting an equal and opposite force on each other. And well, the big bar magnet cannot move because it is big and heavy. So what moves is the freely suspended electromagnet. So we have established now that a current carrying conductor means that the conductor itself is a magnet. It has been converted into a temporary electromagnet. When it is placed in a magnetic field, the current carrying conductor experiences a force. Now, it is very easy to see why it experiences a force, because the current carrying conductor itself has a magnetic field. It has been placed in a magnetic field. Now, the magnetic field has been created by our magnets here, and there is a magnetic field between them in that direction from the north to south pole. And what have we placed inside the magnetic field? We have placed a wire in which current is flowing. So what happens when a current is flowing through the wire? It creates a magnetic field of its own. And the two magnetic fields interact, and one exerts a force on the other. The wire exerts a force on the permanent magnets, and the permanent magnets exert an equal and opposite force on the wire. So this force, clearly, force is a vector. It has magnitude and direction. So now let us talk about how we can determine the magnitude and the direction, because to study both is important. First, we talk about the magnitude of the force. So what do we have here? We have a situation where a current carrying conductor has been placed inside a magnetic field. And we are trying to determine the factors on which the magnitude of the force depends. There are three factors that determine the magnitude of the force. One is the strength of the magnetic field, which is how strong are these magnets? Are they weak magnets? Are they strong magnets? How strong is the magnetic field between these permanent magnets? That's the first question. The second question is, what is the current in the wire? Remember, there is a current flowing through this wire. Otherwise, the wire would not experience a force. So, greater the current, greater the force. So that is the second factor to determine the magnitude of the force. The third one is the length of the wire. The longer the wire, the greater the force. So the force is directly proportional to all three factors: the strength of the magnetic field, the current in the wire, and the length of the wire. So that leads us to this formula to calculate the force on a straight wire carrying a current when placed in a magnetic field. But if the wire makes an angle theta with the magnetic field, what is angle theta? Theta is the angle between the current carrying conductor and the magnetic field. So the formula can be revised and written as F is equal to B into I into L sine theta. Just understand the implications of this. If theta is equal to 0, which means that the wire is parallel to the magnetic field, what does the force become? And when theta is perpendicular to the, or rather when the wire is perpendicular to the magnetic field, theta is 90 degrees. In that case, what does the force become? Think about it. After having discussed the magnitude of the force, we now discuss the direction of the force. Now for this we use what is known as Fleming's left hand rule. Before we go there, I want to add a couple of things. One is, there is a very strong mathematical rigor behind the formula. The left hand rule is merely a convenient way to determine the direction. The mathematics required to express the direction of the force will become clear to you, or will be introduced to you in 12th standard. But a convenient way of determining the force or the direction of the force acting on a wire in a magnetic field is Fleming's left hand rule. And now you have to keep these three fingers, the middle finger, the index finger, and the thumb, perpendicular to each other. So each finger is perpendicular to the other two. And then let us see what these three fingers tell us. So when you hold the three fingers of your left hand up in that way, the left hand rule tells us that the index finger is pointing, if the index finger is pointing in the direction of the magnetic field. Remember, the magnetic field is in that direction. So the index finger is pointing in that direction. Now there is a current carrying conductor and the current is flowing in that direction. So the middle finger is pointing in the direction of the current. If that is the way you hold your left hand and these two fingers, then the direction of the thumb gives you the direction of the force. Remember, we are trying to determine the direction of the force acting on the conductor. We used, earlier we determined the formula to calculate the magnitude. Now we are discussing the direction. So the left hand rule tells us how to determine the direction of the force. What do we have here? We have an electric charge which is moving through a magnetic field, right? And when it enters the magnetic field here. So this is the area which has a magnetic field. So there is no magnetic field here. And therefore it is moving in a straight line. An object on which no force is acting will continue to move in a straight line at constant speed, and that is what it does. But the minute it enters the magnetic field here, it begins to go in a circular path, which basically means that there is a centripetal force in that direction, right? And the centripetal force is caused because of the magnetic field created. So what we have here, these X's indicate that there is a permanent magnetic field which is directed into the surface of the screen or into the surface of the sheet of paper. So it's a three-dimensional situation that you have to imagine. And into that magnetic field, an electric charge is entering. A positive charge moving in a straight line with velocity v enters the magnetic field. And you can use the left-hand rule once again to determine the direction of the force. So this executes a semicircular path. As long as it is in the magnetic field, its direction is constantly changing. Where it leaves the magnetic field here, it begins to move in a straight path once again. This one again is an application of Fleming's left-hand rule. You can use that to determine the direction of the force. So let us do a few practice questions. Carefully read the situations that are described here, and let's see what happens. A positive charge enters a magnetic field at right angles to it. So what it means is the magnetic field is in that direction from the north to south pole, right? And the positive charge moves at right angles to the magnetic field in that way, right? What is the direction of the force acting on the electric charge? What is the direction of the force? Now, if you were to use Fleming's left-hand rule, then you can see that your index finger has to point in that direction, in the direction of the magnetic field. Your middle finger, this is the index finger, the middle finger has to point in that direction because that is the direction of the moving charge or the current, moving positive charge, right? So if you hold your left hand with the three fingers perpendicular to each other in that way, you can see that your thumb will be pointing into the surface of the screen or page. And that tells us what? That the force is acting into the page or into the screen. This is a simple application of Fleming's left-hand rule. A negative charge enters the magnetic field. The situation is similar, but there's just the one difference. This is a negative charge. In the earlier question, it was a positive charge. Once again, we have a magnetic field in that direction, and we will hold our left hand with the index finger pointing in the direction of the magnetic field. We have the electric charge going in this direction, but the critical difference is that it is a negative charge. So earlier we concluded that it was into the screen, but since it is a negative charge, it will be out of the page. The third question, a wire AB carrying a current is placed in a magnetic field. Find the direction of the force on the wire. Remember, all of these are applications of Fleming's left-hand rule, and all of them describe a situation where a current carrying conductor is placed in a magnetic field and therefore experiences a force. So in this case, there is a magnetic field in this direction and the current is in this direction. So if you were to hold up your finger that way, what is the direction of the force? If you imagine your left hand with the 3 fingers, your middle finger pointing in the direction of the current, your index finger pointing in the direction of the magnetic field, then your thumb will be pointing towards you. So the force on the wire is, it seems to come out of the page, out of the surface of the page. What if the direction of the current is reversed? Well, the situation simply reverses and the direction of the force is into the surface of the page. What has happened here is that the north and south poles have been swapped. So this is the direction of the magnetic field. This is the direction of the current. So once again, we can conclude that it is into the surface of the screen. So we have the index finger here, the middle finger here. And when you hold up your fingers in that way, you can see that the thumb is pointing into the surface of the screen. So the force is inside or into the surface of the screen. So in summary, what did we discuss today? We studied the fact that a current carrying conductor creates a magnetic field around it, and therefore when it is placed in an external magnetic field, it experiences a force. It's like bringing 2 magnets near each other. That force has magnitude and direction. The magnitude is given by the formula B I L sine theta. B is the strength of the magnetic field, I is the current in the wire, L is the length of the wire, and theta is the angle between the wire and the magnetic field. The direction of the force is given by Fleming's left-hand rule, which is illustrated here. So that covers another important component of our study of magnetic effect of electric current. Thank you for watching. See you in the next video. Bye.